Hi, my name is Zakaria. I'm a mechanical engineering graduate, and I recently graduated from the National Engineering School of Tunis, University of Tunis El Manar, as one of the top students, which is something I'm really proud of. My diploma is European Engineer Accredited, which is equivalent to a Master's of Engineering in some countries. Everybody knows how engineering is difficult and requires a lot of hard work and focus, and today I'm going to be presenting my end of studies project, which I defended before a jury. I will be doing a voiceover in English since the presentation was in French in order to explain what I did in my end of studies project. That was a 6 months internship in one company. And for obvious confidentiality reasons, I will be hiding the name of the company as well as some details that I had to work on. So I will be presenting the general aspect and explaining what I did and what tools I did use in order to obtain the National Engineering degree. You can clearly see how stressed I am to do this presentation. So without further ado, let's start. Dear jury, thank you for taking the time to judge my work and to evaluate. Dear audience, thank you for attending this presentation. Today I will be presenting my end of studies project named the design and optimization using CFD of an underwater thruster. Let's start by the plan. First of all, we will introduce the project and the context behind it. Secondly, we will do the modeling of the problem and the methodology that I followed in order to obtain my results. Thirdly, we will talk about numerical simulations, how I did the CFD. In the next part, we will talk about the results of these simulations and our interpretations before we go to the next part, which is the mechanical design of the propeller, and lastly, a conclusion about all this product. What I'm keeping about the company is that it's a 3-year-old startup that works on underwater ROVs, which are remotely operated vehicles. They designed a solution to inspect underwater pipelines and offshore platforms. Let's now talk about the context of the project. The propellers have a high price and it's slowing down the development and upgrades of the ROVs. That's why our objective is to design a propeller that fits our needs in terms of power. It means that it has to generate enough thrust as well as resistance to water penetration. It has to be watertight and cost preferably less than what's on the market, thanks to local manufacturing. The workflow that we're going to follow is, first of all, we evaluate a numerical model, then we optimize this model and identify geometric parameters that are important to maximize thrust and answer our needs. Then we will do the mechanical design of the propeller using CAD software. For the physical model, it's a fluid dynamics problem, so we'll be solving partial differential equations that are the conservation of mass, the conservation of energy, as well as the conservation of quantity of movement. These equations have more parameters and variables than there are equations, therefore we need closing equations, which are called turbulence models. Once the system of equations is closed, we will need to add boundary condition as well as initial conditions so that the solution exists and is unique. The way we are solving the partial differential equations are through RANS. RANS is Reynolds Average Navier-Stokes, where the component U, for example, which is the velocity of the fluid, is decomposed into two parts. One average component plus a fluctuant part where turbulences come from. There are different turbulence models. We could name K omega, which is precise, close to the boundary surface, as well as for turbulent flow. K epsilon is more precise, far away from the boundary surface, and is adapted for really turbulent flow. K omega SST combines both of them. It's more complex, but it takes more time to calculate. For computational power and performance reasons, we chose K epsilon as the turbulence model for this problem. The methodology that I followed is the following. First of all, I used ANSA as a preprocessor. It allows me to make meshing with really neat structured mesh. Then we pass on to OpenFOAM to make the numerical simulation before viewing the results on ParaView. It allows us to calculate thrust and resulting forces. Before passing on to SolidWorks, that allows us to modify the geometry and change the parameters. Then, with the new parameters inputted, we go back to ANSA in order to mesh again, calculate again, and visualize the results to estimate the performance. In the numerical simulation, the first step is to mesh our case. We took the real geometry that exists on a real thruster that is on the market. Then we simplified it in order to accelerate and optimize the performance. We put that propeller in a domain using a rotating mesh, which is the cylinder that you see on the top right, and then we made the structured mesh. We made a structured mesh that is really fine, close to the surface, and kind of rough around the edges of the domain. This a zoomed part of the mesh. We can see that the propeller has a structured mesh on the top right. There are quad elements on the surface. They will become hexahedron elements in 3D. Since the geometry is really complex, we cannot mesh with 100% hexahedron elements. That's why we need some tetrahedron elements that will fill in the gaps. We can see that close to the leading edge of the blade, we have really structured mesh. We try to capture the boundary layer effect as good as we can and as well as the performance allows us. This is the structure of the OpenFOAM code. We have the simulation case that has multiple subfolders. The 0 folder contains the initial conditions. U contains conditions on the velocity. P contains the conditions on the pressure. K, epsilon, and newt contain the other variable, for example, the kinetic energy of turbulence K. The folder constant contains the boundary conditions. Polymesh contains our mesh as well as the details about each surface and its boundary condition type. Physical properties contains the property of the fluid, for example, viscosity. Momentum transport is the model of turbulence that we chose. And finally, dynamic mesh dict contains the parameter of the dynamic mesh, something we will be talking about in very shortly. System is the last folders. It contains the general parameters of our simulation. Control dict contains the main simulation parameters, which is, for example, delta t, the incrementation of time, as well as start time, end time, current number, and many other general parameters. FV schemes contains the numerical schemes, and FV solution contains the solver of equation. In our case, I used PimpleFoam to solve the dynamic case simulation. CFD can really be complex, but since it's one of my favorite subjects, I will surely make some videos about it in the future. Back to our presentation. This is the principle of the dynamic mesh. We put the propeller blades inside a cylindrical volume. This cylindrical volume will be rotated. Actually, it's not the fluid that will be rotating, but the mesh itself. After a delta t of time, the mesh will turn by delta theta, the angular rotation speed, omega. So after the point that was initially blue after we moved one node of the mesh, it will take a ponderation between two values. For example, here the blue point and the red point. It will take a value between them. By value, I mean the variables in it, like pressure and velocity, and the other variables will take new values, then recalculate and resolve the fluid equations in this new rotated mesh, and then transport its properties to the next delta t of time, where we will rotate again and recalculate the new properties and variables before resolving the problem again and again. As you can see, this is really complex, but it best describes the real physical phenomena that happens around the blades of the propeller, which could be considered better than a moving reference frame approach, for example. ParaView is our post-processor. It allows us to view the results. We can trace the velocity profiles, for example. We can see the green parts are where the fluid is accelerated, which gives the blades the thrust that it needs. On the left, you can see that the blades are blue, which is a sign of depression. When the pressure lowers on top of the blade and increases on the bottom of it, it creates a gradient of pressure which generates thrust. In the case of a plane, it's called lift, but in our case, it's thrust since it pushes the propeller along its axis. We can also trace streamlines and view how turbulent the flow is. As you can see in the start of the propeller, there is a lot of turbulence, which is normal since the flow is disturbed. Then it stabilizes itself and gives us a proper flow. ParaView also allows us to draw ISO pressure clouds. We can see the depression clouds, which is the zone where the pressure is really low, as well as the high pressure cloud, which shows us the zones where the propeller is pushing the fluid. Actually, the depression cloud allows us to know if our propeller is cavitating or not, which is a phenomenon that really harms the blades of the propeller and causes noise and reduces the performance of our thruster. Before we started our own thruster, we had to evaluate our numerical model. So we took two existing propellers and had to simulate them in order to compare the value simulated with the real value of the propeller that we already own and tested before. The first model gave us 21 newtons of force compared to 24 newtons with the real propeller. It can be considered as close enough. In terms of power, it gave us 67 watts, which is only 60% of the real power consumed, but we must really not forget that we are not taking in the efficiency of the electric motor, the losses due to heat, as well as friction. The second model shows the same results, which is a 85% accuracy on the thrust simulated against a 56% calculated power. This will allow us to take a 50% efficiency on all of our simulations and assume that the electric motor efficiency as well as all the rotating components will take about 50% of the power lost, so then the remaining 50% is transferred to the fluid. These curves show us that by changing the incoming velocity, the fluid velocity overall, which is actually the velocity of the whole ROV, the thrust generated with the same geometry, with the same rotation speed, actually decreases. This is quite normal and predictable, but it gives us a threshold to where to put this decrease in performance. This next diagram shows us how the increase in angular velocity increases power. This will allow us to choose an electric motor by pairing a matching power with a matching angular velocity. Another really important aspect is the shape of the blade. I use different sections with different profiles in order to evaluate performance when changing the profile. I made different leading edge for each propeller as well as different trailing edge and compared the results. For obvious confidentiality reasons, I will not be showing the results, but I will say that one of them has better performance than the others. One of the final parameters that I varied is the angle of attack. Since the profile behaved differently with different angles of attack, I had to change these in order to find the best angle for each configuration. This took a lot of simulations and a lot of tedious work, but I found a certain range where the power and the thrust generated is close enough to what we were expecting and what we were aiming for. Finally, after more than 150 hours of CFD computation and calculation, where 100 hours of those were significant enough to give us acceptable results, we came with the final parameters of our thruster. What I would generally do is that I would change parameters and let my computer run overnight, and then the next morning I would take in the results, put them in, and process them. So at the end, we found a configuration where we were comfortable enough to move on to the mechanical design of our thruster after optimizing the propeller blades for it in the range of power that we were estimating ourselves to be using. Again, I cannot show the details of the electric motor, but all I can say is that it's a BLDC motor, a brushless DC motor. Finally, I moved on to the CAD design on SolidWorks. I designed the body, a front end with double O-rings, as well as a back end that has the electric motor connector, which has its own sealing mechanism. I can finally show the final render of the design. Without showing the insides of it, I am quite satisfied and proud of this result. After sending this design to a local manufacturer and taking into account the electric motor price as well as the different component prices, we estimated the cost to not exceed 600 US dollars. This is a really important value since this propeller performs better than a 1,300 US dollar propeller that is proposed on the market. The next steps in my project is to create a prototype and test it. Unfortunately, 6 months is not enough to do the optimization and CFD parts, as well as the mechanical design part and manufacturing part. We had to wait for the manufacturer to approve our design, and this takes some time. We finally reached our conclusion. I made a propeller with high performance that improves 20% the thrust generated while costing only 50% of the price. This is a really good result, and I'm quite proud of the work that I did. That's all for me. Thank you all for listening attentively to my presentation.
Voilà, merci pour votre attention et connaissance.
Thank you all for staying until the end. I hope that it was instructive and that it was really interesting to watch. I obviously had to answer some questions that were asked by the jury about my presentation as well as my report, which was a very detailed document about my project, about the equations behind everything, and how I did my work. I also explained some details that were not mentioned in the presentation, as well as some mechanical design. This is one of the reasons I made this YouTube channel. It's in order to share my projects as well as my work and to document it for future references. I hope you enjoyed it, and thank you for watching.